Here we go. I will begin with a word of prayer. If I can get through it without coughing. Dearly Father, we thank you for this class. I thank you for this opportunity we have just to study your creation together. Help us to understand it and to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. So, so today we're talking about the Jordan form and diagonalization. So let me just start by mentioning a couple things that essentially we're studying the problem of finding a nice matrix to represent a linear transformation T, which is a transformation from a vector space V to a vector space V over a field, all right? And so we're in the context of a so-called endomorphism, a linear transformation from a vector space to itself. And as we've already described how to find the matrix of this with respect to a choice of basis, right? So what we're going to be endeavoring to do today is to understand how we can make a rather special choice of basis, which puts the matrix of the transformation in a particularly nice form. One of the things I should mention before I forget is one of the results we had in the previous chapter that I didn't mention, I don't think, is that we can define the determinant of a linear transformation, right? And we can define the trace of a linear transformation, all right? And we can define both of those in terms of the matrix of the transformation with respect to some choice of basis, all right? And the reason that's logical, now you should immediately object to this and be like, wait a minute, but the basis, if I chose a different basis, then I'd get a different trace, I'd get a different determinant, right? But the good news is that this is equal to, the determinant of like P inverse T beta beta P, and this is equal to the trace of P inverse T beta beta P, where I'm saying P is the coordinate change matrix to get us to the determinant of the transformation with respect to the bar basis, let's say. And these are properties of the trace and the determinant, namely that they're invariant under a similarity transformation. So we have a freedom here we can exploit, which is we can either look at, as we go through this discussion, we can either stay in the world of linear transformations and abstract vectors, and we can study questions there, or we can study corresponding questions about matrices. They're really interchangeable with respect to a choice of basis. So that's just something to keep in mind. I usually don't know exactly where I'm going to make the transition from one world to the other as I'm lecturing. It just kind of happens, and then I sometimes try to show both worlds, like the linear transformation and the matrix world at once, but that just makes for really cluttered lecturing. So let's make a pact to only talk about one of the viewpoints and let the other one be understood. So that's the first thing. We can talk about determinant of a transformation. We talk about trace of a transformation. But then the next thing I should talk about, and V is going to be a finite dimensional vector space over a field, all right? And so just to keep that in mind, we are going to talk about the difference between the real field and the complex field as we go on, all right? We'll get there. All right, so definition. X, an element of V with x not equals to 0 is eigenvector eigenvector of t with eigenvalue lambda in the field if t of x is equal to lambda x. All right. And we can also talk about the eigenspace, right? So like the eigenspace, let's say E sub lambda is equal to like x such that, you know, t is x such that tx equals to lambda x, all right? Now, there's a slight abuse there in some sense, but not really, which is that that space is an eigenspace in the sense that it has, you know, it has all of the eigenvectors with eigenvalue lambda for t, right? But it does have one other thing. It has 0. So it's a space of eigenvectors and the 0 vector. Fine. That's not really too bad of a, I mean, that's fine. We kind of tend to find these kinds of things, right? Okay, so then the question then is, excuse me, you know, what good do these do you, right? So one example that I might give as a kind of running example here is if we have oh, no, I shouldn't do that. I was thinking about putting the differential equations in here now, but I think it's going to be distracting for reasons I forget about until I get into them. We'll come back to that. We can apply this to solve differential equations, it turns out. I guess I can show that. I'm sorry, Ernesto, I'll get with it here. So a system of differential equations, we could write like this: dx dt equals to ax, all right, where, you know, a is, let's say, an Rn by n. So the goal of this is to solve for x, which is a vector of functions of time, like x1, x2, da da da. All right. So here's the thing: if you know, if there exists, let's say, u, a constant vector, not equal to 0, such that au equals to lambda u, then you can form what's called an eigensolution. X equals to e to the lambda t times u solves our system of differential equations. So now here I've already shifted viewpoints, haven't I? Because I'm talking about the eigenvector of a matrix rather than a transformation. But what is the correspondence? The eigenvector of the matrix A is exactly the eigenvector of the left multiplication by A map. It solves this equation anyway. So if you have this equation, right, if you differentiate this, what happens? Well, dx dt, what's the derivative of e to the lambda t? Well, that's lambda e to the lambda t, right? And u is a constant vector, so it just rides along. And then, well, lo and behold, you got yourself, you know, you got the lambda and the u, those go together to give you what? They give you, you know, a e to the lambda t u. See, because lambda u is equal to au, right? Which then means this is equal to ax, which means, hooray, we solved it. So if you can write your system of differential equations as a matrix column product, and you always can, Even if it's a higher order differential equation, you can always do reduction of order and convert it into a system of first order differential equations. So this is actually very general. But I'm trying to talk mostly about the Jordan form today, so let me not get into all that. My point to you is simply that eigenvectors of the matrix give us solutions to the differential equation, right? And I'll just tell you this much. If we could find n linearly independent eigenvectors, right? If you could find not just one u, but a collection of n of them, and they were all linearly independent, then the existence and uniqueness theory of differential equations would say that the general solution of this problem is just given by a linear combination of these eigen solutions. So if we can find a set of vectors which serve as eigenvectors for A, and those eigenvectors are linearly independent, that makes us be able to solve the differential equation with a linear combination of eigensolutions. It also would be the case that that kind of matrix is diagonalizable. So let's look at that. All right. Let's look at that for a second here. Can I erase? Okay. So, theorem. If T has eigenvectors, you know, u1, u2, dot, 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 un, forming linearly independent set, then, well, for one thing, if that's the case, that makes this beta, and thinking collectively as a set, and so-called eigenbasis. An eigenbasis is a basis of eigenvectors. Eigenbasis for T. This is all done with respect to a transformation T, right? It's all tied to a given linear transformation. And then in an eigenbasis, you can calculate the matrix of T with respect to this, right? And what happens? Well, remember how it goes. We do the coordinate vector of T of u1 with respect to the beta basis, the coordinate vector of T of u2 with respect to the beta basis, and so forth and so on. But what are these respectively? Well, that's lambda 1 times u1, lambda 2 times u2, lambda n times un. So I guess I didn't say it before I wrote it just now, but let it be understood that it's an eigenbasis for T with eigenvalues lambda 1, lambda 2, dot, 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 lambda n respective. And again, these are all scalars in the field. I've yet to even entertain the question of how do you find which scalars are allowed, right? I'm just at the moment just saying, well, suppose you got them. What can we say about it if you can find them? Now, it would be ever so embarrassing after this discussion if we found out that you can't even find any. That would be annoying, right? But that's not going to be the case. You can find them, always, except when you can't. But so anyway, that's lambda 1 e1, lambda 2 e2, lambda n en, also known as the diagonal matrix with lambdas down the diagonal like that. Definition: a transformation is diagonalizable if and only if there exists an eigenbasis for the transformation. You see, that's a good definition, because if there is an eigenbasis, it means that with respect to that choice of basis, the matrix of the transformation is diagonal. Right? Of course, there's other things we can glean from this, right? Like, corollary. For T diagonalizable, the determinant of T is the product I equals 1 to n of the eigenvalues, and the trace of T is equal to the sum I equals 1 to n of the eigenvalues. So the determinant is the product of the eigenvalues, and the trace is the sum. And that's immediate from the form of the matrix in the eigenbasis. Do you see? Do you see why? Like, what's the determinant of this matrix? It's product. What's the trace? Sum, right? The fascinating thing is, not every matrix, not every transformation is diagonalizable. And yet, these formulas are generally true.
What do you mean they're general?
If you don't say diagonalizable, just given T an endomorphism, these formulas are true. Even if there doesn't exist eigenvalues, if you're dealing with a transformation over the real field, and there are no eigenvalues because you just don't have any, because it's real. Because what you'd like to be your eigenvalues, they're complex. Well, the thing is, in that context, they come in conjugate pairs, and it still works out to make sense. Because the product of the conjugate pairs works out to be real, and the sum of the conjugate pairs works out to be real. And it's still true in the context that you don't even have eigenvalues for a real transformation. To prove that, we need to look at what's called the real Jordan form, which is a terribly neglected topic in abstract linear algebra because it's ugly. And algebraists like to make things prettier than they are.
So in the transformation over the complex numbers, do we always have eigen?
Ah, good question. So the question was, do we always have eigenvalues if our transformation is over complex numbers? So the question is, what are eigenvalues, right? So theorem, but the answer to your question is yes. For a transformation over the complex field, we always have eigenvalues. The reason for that will become glaringly obvious in a second here. But let's say it this way. Lambda in the field is eigenvalue for T from V to V, right, over F, if and only if the determinant of lambda times the identity on V minus T is equal to 0. So let us introduce the characteristic polynomial of T in the T variable is going to be equal to the determinant of T. Let me use it. Well, I'm stuck with it. Man. Too many T's. Let me change the variable to S here for a second. Curses. I'll make my transformation something other than T. I'm going to make my transformation S here. The characteristic of the S transformation would be the determinant of T times the identity on V minus S. This is the so-called characteristic polynomial. Of S. Now, opinions vary on this matter. There's two choices you can go by here. You can either make the characteristic polynomial monic, which means its leading coefficient is 1, or you can reverse that and do S minus T times the identity. In the teaching of undergraduate linear algebra, I gravitate towards putting S minus t times the identity because there's less sign errors to make. So as a kindness to the students, I do minus the identity. But from a pure math perspective, this is what we should write. Now, so the characteristic polynomial is a very important character in this game. But let's prove this theorem. Okay? So proof. I hope I've stated the theorem correctly. We'll find out soon. So if, you know, Tx is equal to lambda x for some x not equals to 0, right? Then lambda minus t times x is equal to 0, right? And lambda minus t times 0 is equal to 0. Therefore what? X is non-zero. That's a solution to that homogeneous equation, right? But it also is a homogeneous equation, so it has a 0 solution. Uh-oh. There's 2 solutions to the homogeneous equation. That means the kernel's non-trivial, which means the function's not one-to-one, which means that this is not an invertible transformation, which means that the determinant of lambda minus t is equal to 0. In other words, if I take the characteristic polynomial of t and I evaluate it at lambda, I get 0. If I put t equals to lambda, it's a 0 of that equation. So you know what I'm referencing, right? Like if we have a linear transformation and it doesn't have a unique solution for 0, that means the inverse doesn't exist. But if the inverse doesn't exist for a transformation on a finite dimensional space, that means that the transformation has a determinant which is not 0. Excuse me, other way around. It has to be 0. If the determinant's non-zero, that means the inverse exists. And we can calculate the formula for it by the classical adjoint formula and junk. Okay, so that is that away, right? I was sure about this I'm a little less, I feel like I may have, I'm not sure I've stated it clearly the other way. So the other way, suppose that well, I mean, so we have determinant of lambda times, you know, and listen, I'm just going to write that as lambda minus t because I'm getting tired of writing the identity map there. Okay, is that okay? I mean, this implies that lambda minus t, you know, inverse does not exist. I mean, we don't even have to go to that. Let's just get straight to the point. It's not that the inverse doesn't exist. That's really the interesting thing. The interesting thing is that that means it must have a non-unique solution. That means that, you know, lambda minus t times x equals to 0 has more than just x equals 0 solution, right? In other words, there exists x not equal to 0 such that, you know, lambda minus t times x acting on x is equal to 0, which of course is to say that, you know, t of x is equal to lambda x, which is to say that lambda is eigenvalue for t.
And this we got from the matrix, invertible matrix here.
Sorry. Yeah, we have it from that list of equivalent statements characterizing the non-invertibility of a, you know, the critical one for us. And that one seemed really boring. back at the start of the matrix theory, like, oh, the homogeneous solution has more than one solution. Or more to the point, the homogeneous equation has a non-zero solution. That means that the matrix is not invertible. That means that the matrix has determinant 0. It didn't seem that interesting at the start of the course, but it becomes of primary importance here. Actually, when you get into the nuts and bolts of proving fussy stuff about the equivalence of invertible matrix and so forth, that theorem that the homogeneous equation has only the 0 solution is often a really, really convenient one to use. But okay, so if you look at this, we actually have a little bit more. There's a little bit more that you can glean from this proof, right? Which is what? So like corollary, if we calculate the characteristic polynomial of a linear transformation, I'm going to call it S, you know, if that of lambda is equal to 0, then the dimension of the eigenspace of lambda is greater than or equal to 1. In other words, there is at least one eigenvector. And what, by the way, what can else, just from an algebra perspective, what can we say about that? What does it mean for characteristic S? What does that mean if we drop back to, like, I'm thinking of lambda as a fixed root, but I'm going to think about this in terms of the variable t. Well, this here, in terms of the factor theorem, means that t minus lambda is a factor of this, right? So if you have a factor corresponding to 0 lambda and the factorization of your characteristic polynomial, you necessarily have an eigenspace of at least dimension 1. Because there has to be at least one non-zero vector, right? Now there could be many. So far so good? So for a specific problem, the task of finding eigenvectors is pretty straightforward, right? What you do is you take the transformation, you're working with respect to some basis, you write down the characteristic equation, and you try to factor it. And then for each eigenvalue you get in the factorization, you try to find an eigenvector corresponding to that eigenvalue. And if you get n of them, well, you got an eigenbasis that's diagonalizable. But if you can't find n of them, then you know something's up. All right.
You're wondering what the correct base is.
But we'll do an example. Let's do an example. So, example 1, we'll let t of x comma y equal to cosine theta minus sine theta cosine theta, right, times xy. So the characteristic polynomial here of t with respect to the t variable would be like determinant of t minus cosine theta sine theta minus sine theta t minus cos theta, which here would be t minus cosine theta squared plus sine squared theta. So this equals to 0 if and only if theta is an element of, you know, pi z. So unless the parameter theta happens to be a multiple of pi, this transformation has no real eigenvalues. So here I'm, of course, thinking of T as a mapping from R2 to R2 for the sake of specificity. I wanted to show you an example of a linear transformation which has no eigenvector. And this is totally unsurprising, because if you think about it geometrically, what is this? Though this is a rotation, right? So if we picture V, you know, which would be like xy, let's say, and then you picture T of V, what does it look like? Well, maybe over here, right? You're rotating by angle theta, you know? So think about that. Can that be what's an eigenvector? An eigenvector is a vector that when you feed it into the mapping, it comes back as simply a scalar multiple of the input. It's kind of like a fixed point. It's not quite a fixed point. By the way, eigen is just like German for proper. It's a proper vector. So, you know, these things were invented back when Germany still had like influence and hadn't like squandered their World War II happened, you know. Also, we stole all their scientists and junk. And Göttingen became Princeton, I guess. I don't know. But so obviously, this can't be a scalar multiple of that unless what? Unless it's either 0, that's the identity transformation, or it's pi, in which case it's just eigenvalue minus 1. Boop, boop. All right, but other than that, no eigen, right? Which means that this matrix, cosine minus sine, sine cosine, is a quintessential example of a non-diagonalizable 2 by 2 matrix. It's not diagonalizable in the real sense, okay? As we go on today, I'll introduce something called the complexification of a space, and we'll see that you can take any vector, any linear transformation on a real vector space, and you can elevate it to a linear transformation on the complexification of the space. And the complexified vector then is a linear transformation on a complex vector space, and as such always has eigenvalues. And then there's a systematic way of taking the basis of the complex eigenvalues and eigenvectors for the complexified transformation and reading back into that a beautiful and simple basis for your original real transformation. This, in a nutshell, is the content of the real Jordan form. But anyway, so the other example, we'll get back to that. We'll get back to that. Example 2, and I'm going to make this like super easy, all right, would be something like T of x, y, z equal to, oh, I don't know, 1, 2, 3, and, oh, my bad. I should have put 1, 2, 2. All right, 1, 2, 2. And I'll put a 1 here, and I'll put zeros over here. So I'm being very lazy, Ernesto. I'm doing things that make the calculations super nice, all right? So this time, what's the characteristic polynomial of t this time? Characteristic of t, determinant of t minus 1, 0, 0, 0, t minus 2, 1, 0, 0, t minus 2, right? Which is just t minus 1 times t minus 2 squared. Something I should have pointed out. What's the degree of the characteristic polynomial? The degree of the characteristic polynomial of an endomorphism is equal to the dimension of the vector space on which the endomorphism is mapping. So on a 2-dimensional space, you have a quadratic characteristic polynomial. On a 3-dimensional space, you have a cubic characteristic polynomial. And so the story goes, it gets worse. So at the base of everything, you got to factor a cubic, or factor a quartic, or factor a quintic, or factor. You get the, yeah. It's bad, but nevertheless, there is systematic calculations that can be done here. And of course, there have been people who have made their careers of trying to approximate this numerically. But this is a very fussy thing from a numerical perspective. Like this, like the eigen stuff, it's not numerically stable. You change it just a little bit. Like, if you have, well, just take a simpler example. If you have a matrix which is not invertible, right? All you have to do is perturb it ever so slightly, it becomes invertible. So like numerical methods and the matrix algebra, it is a precarious business. It's very sensitive to machine error, and you know, it's probably an art to do that well and yet do it fast. But anyway, so we see that we have, let's say lambda 1 equals to 1 and lambda 2 equals to 2. Let me introduce some terminology. The multiplicity of the eigenvalue in the characteristic polynomial is called the algebraic multiplicity. So this has algebraic multiplicity 1. This has algebraic multiplicity 2. I couldn't even talk about multiplicity of eigenvalues in the previous example because there were no eigenvalues. All right. So then, if we study, so let's call this matrix A. All right. Basically, my T is left multiplication by A in this case, right? Fine. What are the eigen? We want to solve. Basically, we want to solve AU1 equal to U1, but you know, it is just better to solve A minus I times U1 equals to 0. This is just a better equation to try to solve. Okay? Like homogeneous equations are easier to solve than this. Never solve this. So anyway, if I subtract 1, what do I get? I've got myself a 0, 0, 0, 0, 1, 1, 0, 0, 1 times my U1 vector, right? And for the sake of calculation, let's say U1 is UVW. I usually use like UVW as like disposable variables in these kind of calculations. So my U1 has a vector symbol on it just because otherwise I run out of letters here. But if this is equal to 0, 0, 0, you can pretty much read off the solution from this. U1 should be equal to what? What would work here? If you look at this, the third equation forces W to be 0, which then forces the V to be 0, which means, well, the first equation's the trivial equation. So put this all together, this means that U is free, which means we can make U whatever we want. The one thing we can't make it is 0. That would give us the 0 vector. That's not allowed. So I'd make it 1. In other words, the first standard basis element is an eigenvector with eigenvalue 1 here. All right, and you can try it out. What happens if we calculate AE2? What's it equal to? AE2 would be the second column, right, which would be 0, 2, 0, which would be 2E2. So column 2 of A is that. So that means E2 is an eigenvector with eigenvalue 2. But what I really should have done is looked at the eigen equation just to show you that that's it. So like here we go. So A minus 2I times, let's say, U2 would be equal to minus 1, 0, 0, 0, 0, 1, 0, 0, 0 times a disposable variable UVW, which is my U2, right? Now this is all equal to 0. What is this? Are there any other solutions other? Are there any other solutions other than E2? Like, let's think about this. What does this tell us? This tells us the top equation tells me that U equals to 0, right? The next equation, I get that W is equal to 0. So V, free. So that means that U2 looks like 0, V, 0, which means it's a non-zero scalar multiple of 0, 1, 0. By the way, in the pursuit of eigenvectors, we don't really care about scalar multiples. You know, we just want to find one. So I usually just make it length 1 if I can. So long story short, this E2 I guessed by just looking at it. Not only is it an eigenvector with eigenvalue 2, it is the only eigenvector with eigenvalue 2 up to linear independence. Of course, there's infinitely many eigenvectors with eigenvalue 2 because any scalar multiple of E2 is also an eigenvector with eigenvalue 2. But it is nevertheless the case from this calculation right here, you should be able to see that the dimension of the lambda 2 eigenspace, right, is equal to 1. In fact, E lambda 2 is the span of E2, right? So, what does this all mean? Well, what this means is that this matrix, this transformation, is also not diagonalizable. But this matrix, this transformation, is not diagonalizable for different reasons than example 1. Example 1, we just couldn't solve the characteristic equation. Example 2, we can't find enough eigenvectors. So if I was to try to solve the system of differential equations, like what system of differential equations would correspond to example 2? So you'd be up against, here's what it would look like. It would look like dx dt equals to x, dy dt equals to 2x plus y, and dz dt is equal to 2z. This system of differential equations, this is the system of differential equations with a equal to, 1, 0, 0, 0, 2, 1, 0, 0, 2. And that system of differential equations, I cannot get, see, like, so the theory of differential equations said you need 3 linearly independent solutions. And, like, you can't, there's not enough. You can find 2 eigensolutions, right? Like, I can write down, R of t is equal to like c1 e to the t times 1, 0, 0 plus c2 e to the 2t 0, 1, 0. All right? And that's lovely, but that's not a general solution because it's a third order problem. I mean, rather, it's a system of 3 differential equations. The general solution must contain 3 linearly independent solutions. That's only 2. The third one we haven't got yet. So what goes here? All right. I'll try to come back to that.
How is the other things
Oh, this? It's just that that's the same as dr dt equal to the matrix 1, 0, 0. Oh, my bad. Yes. That should be a z. Man, so sorry. Thank you. Very good question. Yeah. All right. Okay, so Check my mic. Sure, we're not out of batteries. That would be sad. Oh, I'm still jibber jabbering. All right, so far so good.
Yes.
So the there are lots of like really beautiful theorems about eigenvalues and like linear independence properties. So like let's see here. Let's see. I'm trying to find my. Come on. Where are you going to? Yep. Mm-hmm. Okay. I'll get there eventually. Now, so the dimension of the eigenspace is the geometric multiplicity. The number of times the factors repeated is the algebraic multiplicity. And the theorem that basically governs these is, first of all, the algebraic, the geometric multiplicity has to be at least 1, and it can be at most the algebraic multiplicity. But it doesn't have to be. As you can see here, the algebraic multiplicity was 2, but the geometric multiplicity was 1. But one of the theorems that we could prove, but if I know what's good for me, I probably won't prove it today, right? Is that all right, I'll try to save. Let me write it up here to save it. Right, I'll try to save it up here. So I'll keep this guy up here to remind myself to come back to it, okay? Ooh, wonder if I... Oh well.
Plus.
Yeah, probably. Let's just suppose it was in frame. It's all right. All right. So anyway, I guess you get what you pay for, right? So so this is my theorem 8.1.23. Basically says that if you know, the algebraic multiplicity of lambda for t is, let's say, m, then 1 is less than or equal to the dimension of the lambda eigenspace is less than or equal to m. Right. And of course, just a reminder, this is the so-called geometric multiplicity. The proof of this is actually somewhat involved, and it involves like block matrices and things. So it does take me about 15 good minutes to prove this properly. It's not entirely trivial. Another theorem is that if lambda 1 is not equal to lambda 2, then e lambda 1 and e lambda 2 both non-zero, okay? Both non-zero. I'm assuming they're non-zero. it's a stupid thing, but if you take lambda not an eigenvalue and you just extend my notation, it still makes sense. Like, what's the what's the solution for, you know, t of x equal to lambda x, where lambda is not an eigenvalue? Well, it's just 0. So this is only interesting. E sub lambda is only interesting if lambda is an eigenvalue. So both non-zero are independent subspaces. So, which is to say that eigenvectors with different eigenvalues are linearly independent. If you have a collection of eigenvectors with eigenvalue lambda 1, and you have a collection of eigenvectors with eigenvalue lambda 2, any linear combination of these two, linearly independent from one another. In other words, you could write that, you know, E lambda 1 plus E lambda 2 is actually equal to what? E lambda 1 direct sum E lambda 2, right? So furthermore, for distinct lambda 1, lambda 2, dot, 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 let's say lambda s, if, you know, E lambda 1 plus E lambda 2 plus dot, 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 plus E lambda s is equal to V, then T is diagonalizable. And of course, these are all with respect to a given endomorphism T on a vector space V, right? I mean, that's assumed here. So like example 2 exhibits this not happening, because if we took, in example 2, if we took E lambda 1 plus E lambda 2, we didn't get all of our 3. We just got a subspace. On the other hand, you can also see that the eigenvectors in the 1 and the 2 direction in my example 2, they are nevertheless linearly independent. Not an accident. So in the course, I usually spend like a full hour proving linear independence of eigenvectors, but I am too sick to do that. Nothing good will come of me trying to prove any part of that. I do have some explicit calculations in the notes, though. Like if you look at my proof of theorem 8.1.27, there I have distinct eigenvalues and corresponding, you know, set of distinct eigenvectors. Then I prove that they form a linearly independent set. This is usually proved by like contradiction or induction or something. The proof in my notes on page 226 is just a calculation. It's just a calculation.
Did you say 8.1?
Theorem 8.1.27, which is a lower form of what I wrote on the board. Because what I wrote on the board is the theorem for eigenspaces. And that would be my theorem 8.1.28. So, yeah, really, if you look at theorem 8.1.28, that is a more full statement of what I'm writing on the board. And that's on page 228. Basically, what I say there is simply this. If T is diagonalizable, if and only if V is the direct sum of eigenspaces for T. All right. And if that is the case, the characteristic polynomial, what that also means, this also will mean that every algebraic and geometric multiplicity will match. And I don't mean, I mean eigenvalue by eigenvalue, right? One eigenvalue at a time. See, because if even one of them doesn't match, that signifies that you didn't have as many eigenvectors geometrically as you had algebraically, which means you're missing something, which means you can't form an eigenbasis. All right. So, what then? What then do we do? In the context, so like, okay, great, there are many transformations that are diagonalizable. We'll see in the next chapter, hopefully like, you know, a little bit later this week, that here's a simple criteria that implies, perhaps the most simple criteria I can tell you that implies diagonalizability. This is just an amazing theorem. If A transpose is equal to A, then A is orthonormally diagonalizable. In other words, this theorem says that theorem 8.1.28 happens, there are enough eigenvectors. And not only that, it says that you can choose an eigenbasis that is also all length 1 and perpendicular in the generalized sense of perpendicular we'll talk about in the future lecture. This is an amazing theorem. This is the real spectral theorem. Real spectral theorem. It also implies that the eigenvalues of a symmetric matrix are all real. They're all real. So symmetric matrices are just incredibly nice.
What is orthonormally diagonalizing?
We'll talk about that. But it means that every vector has length 1 and the dot product between any distinct pair is 0. So like, you know, the standard basis is orthonormal, for example. But we will generalize that concept for an abstract vector space paired with a what's called an inner product. All right? Okay, so just to say, there is a vast context where this happens. It's nice, it works out. But what happens when it doesn't? All right, and that brings us to the next. There's two things we have to talk about. There's two very different directions. One thing we have to remedy example 1. Right, we have to talk about the complexification. The other thing we have to do, though, is we have to remedy example 2. And this brings us to what's called the Jordan form. All right? So it's a pretty good place to break the video.